Good morning. Today we will discuss about Walsh functions. In the last lecture, we have seen about Fourier transforms. We have gone through two different types of Fourier transforms: a full cycle window based DFT, and we have also seen half cycle window based DFT. These two techniques were employed to determine phases, right? So based upon the digital data which we do have, discrete data, we were able to estimate the phases, both the magnitude and also the phase angle of not only the fundamental components. We were able to estimate the DC components and also higher order harmonics also. So we have done problems on these things, and we have done a quick comparison on these two methods. In today's class, we will discuss about Walsh series, a new type of technique which is used for determining the phasor. So in today's class, we will have a quick introduction of Walsh functions. I hope that by the end of this lecture, you will be able to describe the properties of Walsh function and also determine the Walsh coefficients. So I'll start with the definition of Walsh functions, and then we will move on to fundamental properties of Walsh functions, and then we will see how these Walsh functions are represented, and finally we'll close the session with the Walsh series, how it will be written. Coming to the introduction part of Walsh series, you know that the Fourier series, it enables any periodic function to get resolved into a summation of discrete sinusoidal components. Now let us suppose any f of any function is there. Then with the help of Fourier series, you can resolve it into any periodic function. It can be resolved into summation of discrete sinusoidal components. This is what we have learned with the Fourier series. Now, an alternate approach for representation of this periodic function in this sinusoidal components, we can go with orthogonal components also. And this type of mechanism is called as Walsh series. And these functions are called as Walsh functions. So rather than representing them in terms of sinusoidal components, we are representing them in terms of orthogonal square waves. I'll write it clearly. It is orthogonal square waves. That I'll show in the next slides. So whenever, most of the times, the signals do take pulse type of representations also. So when the signals do take a logic pulses, they do take the form of logic pulses, which are basically fundamentally rectangular in nature. Then Walsh functions can be employed. So these can be employed when the signals take the form of logic pulses, which are basically rectangular in nature. Now, on the other hand, rather than generating the sinusoidal pulses, it is easier for us to generate a square type of train, square pulses, or what we call them, because when we think about generating a sinusoidal technique, we need to write a particular equation. It is just like sine omega t. But whereas in case of a square pulse train, what all you need is nothing but just only represent. It will be just like here. You need to represent only this particular value from this duration to this duration. Whereas for a sinusoidal one, then you need to represent this one, and you need to represent the frequency, etc. So it is easier to generate square pulse trains because the data which we are supposed to give it as input is very small, and so it is relatively easy to construct and also analyze a given waveform using the Walsh techniques when compared to the Fourier techniques. Now, the Walsh function, generally it will be written in the form of Walsh k of t by t, and it will be having a magnitude of +1 or -1, and this particular function indicates that in the time interval of t, this is the time interval, this function is crossing the time axis k number of times. So k indicates the number of times it changes the sign per unit interval t is equal to k. Okay. So I'll show you in the next figure that the first 8 Walsh functions of integral index k for the time which is less than periodicity. Normally, the number of sign changes per unit time, we call it as sequency. Just like you represent as frequency in terms of sinusoidal terms, here we call it as a sequency. Sequency formula is number of crossings of time axis in the given time period. This is sequency. Now, see here, this is K0, K1, K2, K3, K4, K5, K6, K7. This is what I have written here. See. Now let us suppose if I take this as the periodicity or the time period which I am going to consider. See how many times it has crossed the time axis? 0. So that's why it is called a 0. Here 1. Here how many times? 2, 3, 4, 5. Here 1, 2, 3, 4, 5, 6. So 6. And here it is 7. If you carefully see, it is 7. Then you might be getting a question, sir, why these things are very different. In the next lecture, in the next slide, you will come to know that normally what happens is these Walsh functions, they exhibit odd or even symmetry. If k is an even number, then it exhibits even symmetry. If k is an odd number, then automatically it exhibits an odd symmetry. So you know that what you mean by odd symmetry or even symmetry. Very simple. Now let us suppose if I do represent it this one, right? So what is, now let us suppose it is a half. So now you say me whether it is an odd symmetry or an even symmetry. This one is basically an odd symmetry because if you fold this one in this fashion, now if you carefully see, this one is quite opposite to that of this one in terms of sign. So it is called as odd symmetry. Now let us suppose if I write it this one like this. Now if I fold this one here, now both are same, right? So it is called as even symmetry. So that's why if you carefully see, for Walsh this is an even function. So k is equal to 0, it is considered to be an even now. So if you carefully see, if I fold it in the middle, both are same. But whereas since it is odd, if I fold it here, so if you carefully see, it is odd symmetry, right? Now here also in 2, if I fold it here, now you'll get even symmetry. Now it is 3, it is odd symmetry, right? So similarly, now this is, see, this is odd number, right? So that's why I'll be getting an odd symmetry here, right? So this is even symmetry. Now this is odd symmetry. So like that, it depends upon the number which you'll be using, right? So now we will move on to the fundamental properties of Walsh functions, index and time scale. So this is first property which we will be discussing. See, doubling the index of Walsh function is equivalent to compressing the time scale by a factor of half. So if I double this one, then automatically it means that it is just compressing the entire time period by half. Now I'll show you in this picture itself. Now if you carefully see, I'll take, this is 2, right? K is equal to 2. Now I'll consider k is equal to 4 now. Now if you carefully see, in k is equal to 2 to k is equal to 4, k is equal to 2, now you do have, it is just like, if I divide it into 4 halves, This is first half positive, first quarter it is positive, second quarter negative, third quarter is negative, fourth quarter is positive, right? Now I am doubling this k value to here. Now it is just like, if you carefully see, if I divide it into half, I am dividing the periodicity into half. Now you see this particular one, it is very symmetrical to that of this particular waveform, isn't it? So which means that doubling the value of k indicates that you are just reducing the periodicity. Both have a very similar wave. Similarly, you can go with 1 and 2 also. See, 1 and 2. If I divide it into half, see, this is the same waveform which I will be getting. So the first function is index and time scale. If you double the index, then automatically time scale is just reduced. The second one is a multiplication one. When two Walsh functions are multiplied together, another Walsh function is produced, such that, let us suppose if I multiply these two functions. Now h is one index and k is one index. So h and k are two indices. If you are going to multiply that one, then automatically you will get a number here, an index here, which is just like it will be having a binary value which is equal to, if both the binary numerals of h and k are alike, then it will be having a 0, and it has 1 if both are different. Now I'll explain it to you with an example. So let us suppose if I take Walsh is equal to, let us suppose 2 comma t by t, and the other I'll take Walsh 4 comma t by t. Now if I want to multiply these two, then let us suppose I'll take the order of 8, which means it is 2 cube. So which means I am supposed to represent it in 3-point binary format. So 2, if I represent it as in binary formats, it is 0, 1, 0, right? 4, it is 1, 0, 0, right? So the resultant number will be 0. If both the numbers are same, then I will be getting 0. Now different or that, then I will be getting 1. So what is 1, 1, 0? It is 5. So if I multiply these two, then I will be getting Walsh of 5 comma t by t. This is the convolution mechanism, multiplication mechanism. Now see here, here they have taken 3 and 5 of the order 8, let us suppose. So 3 can be represented as 0, 1, 1. 5 will be represented as 1, 1, 0. Sorry, 1, 0, 1, right? So I think, yeah, I think it is 1, 1, 0 is 6, I think, right? So sorry, it is 6, yeah. So 5 means 1, 0, 1. Now if you do 1, 1, 0, it is 0. Different numbers, you will get 1, 0, 1, here it is 1. So this will represent 6. So multiplication of these two will be giving you a 6 number, right? So like this. Next one is symmetry. As I already mentioned, it can be concluded that they do exhibit even or odd symmetry with respect to half of the periodicity, depending upon whether k is even or odd. If k is odd, then they will represent odd symmetry. If k is even, then they will represent even symmetry. Next is discrete representation of Walsh functions. In most of the applications, digital applications, we generally represent Walsh functions in discrete form. So let's n be the number of samples per unit interval. Let us suppose if you do have a signal, then n is the number of samples per unit interval. So the length of the discrete Walsh function will become n, just like you have done in Fourier series. N indicates the number of samples in a given time interval. Now, how you represent that one? How you represent the Walsh function in that particular one? Now, let us suppose whatever the number of samples which you are getting, it is equal to n, and it can be represented as a power of 2. Now, the discrete Walsh function, okay, Walsh k of, this is what we have been using in the past equations also. So, how to determine this particular value? See, this is the formula. It is pi r is equal to 0 to p, where p is this particular value. If you represent n as a power of 2, then whatever the power which you are getting, that is 1. Minus 1 to the power of k p minus r plus k p minus r minus 1 j r. Then what is this one and what is this one? Right? So k and j, they are supposed to be written in binary formats. Now let us suppose if I want to take Walsh 5, 4, then what I must do? I must represent this one in binary format. 4 is also to be represented in binary format. How many bits you are supposed to consider? This many number of bits you are supposed to consider. And based upon that, you are supposed to calculate the Walsh function. That we will see a problem now. Okay. So this is the representation of Walsh function, where k and j are to be represented as binary series. This is what it represents. K and j are to be represented as binary series, and the k, r, and j are the bits of the binary representation. That we will see in the problem. Okay. So in the next lecture, we will see problems on this particular.